Okay, algebraic expressions. Okay, in this section, we will be covering how to add and subtract polynomials, multiplying algebraic expressions, and special product formulas. Okay, algebraic expressions. So a variable is a letter that can represent any number from a given set of numbers. If we start with variables such as x, y, and z, and some real numbers, and combine them using addition, subtraction, multiplication, division, powers and roots, we obtain algebraic expressions. So here are some examples of algebraic expressions. To be clear, there should be some commas here. So this is one of them. This is an algebraic expression, 2x squared minus 3x plus 4. Here is a separate algebraic expression, square root of x plus 10, for example. And here's another one, which is a giant fraction, a rational statement. Y minus 2z divided by y squared plus 4. Notice that in all of these cases, there is no equal sign. That's really the main difference between an algebraic expression, it's like a statement, and something that's an equation that has an equal sign. So don't confuse the two. So in particular, we care about something called monomials. A monomial is an expression of the form a times x to the k power, where a is a real number and k is a non-negative integer. So I know there's a lot of letters there, but anything that fits this form, let's look at examples that fit this particular form, ax to the k. So for example, if we had like 3x to the power of 2, this would fit this form where the a is a 3 and the k is a 2. Or say 5x to the power of 7. That would be another example. Now there's nothing special about the letter x. We just use the letter x as our independent variable a lot. Math really likes to use the letter x. So later we'll run into other situations where there are other variables such as a y or a z that represent the independent variable, where a and k in this case represent constants. Okay. All right. So looking at this little these expressions up here, this one in particular fits the form. So 2x to the power of 2 fits the form of a monomial. The minus 3x also fits the form. This is where the k is a 1, right? By default, if there's nothing there, then there's a little 1. And even the basic number 4, just the number 4, fits the form because 4 is the same thing as 4x to the power of 0. Right? So k is allowed to be a non-negative integer. That just means it's allowed to be 0. And remember that x to the 0 power is a 1, so 4 is the same thing as 4x to the 0 power, and therefore it fits this form. The things that do not fit this form are cases where the k is a negative. So for example, if we had 3x to the negative 2 power, now it is no longer a monomial, right? Because of that. It's still an algebraic expression, so we can still say it's an expression. It's just not a monomial. Monomial is a special kind of an algebraic expression. So no negatives, no decimals. So if we had 5x to the 0.2, that's not allowed. It's not a monomial. It's got to be a counting number. That's 1, 2, 3, 4, 5, and so on, or a 0. But no negatives, no decimals, no fractions. So if we had 7x to the 1/2 power, that's not allowed, right? That's because this is the same thing as square root of x, right? This equals 7 square root of x, and neither of those qualify as a monomial. Right, so a very specific group of things. So a very specific group of things fit this form. It has to be a multiplication between a number. The a is a number, any number, positive, negative, decimals. Right, so decimals are allowed for that part of it. So if we had 0.2x to the power of 4, that would be okay. You're allowed to have a decimal, let's put that there, a decimal times x to the power of 4. So the a is allowed to be a decimal. It's just that the k has to be a 0 or a 1 or a 2 or a 3 or a 4, a counting number. a non-negative integer. Okay, so once we know what a monomial is, we can put together addition or subtractions of monomials and come up with algebraic expressions of the form of this form. So a binomial is a sum of two monomials, and a trinomial is a sum of three monomials. Right? We can keep going with that nomenclature for the summation of monomials, but really we don't use it beyond three. So binomials and trinomials are very, very popular, or the naming scheme referring to them that way is very, very common. But beyond that, we don't really think about quadnomials or quinnomials and all that. We kind of stop there and just generally refer to them as polynomials. So polynomial is just a generic term that means the addition or subtraction of any number of monomials. Whereas if you're specifically only adding two of them, then we call it a binomial. And if we're specifically adding or subtracting three of them, we call it a trinomial. For example, the first expression listed above is a polynomial, but the other two are not. So referring to these three statements, all of them are algebraic expressions, but only this one qualifies as a polynomial. It's a summation of three monomials, right? Each one of these independently qualifies as a monomial. So the whole thing is a trinomial because we're adding or subtracting three monomials. And then in general, we can just say it's a polynomial. Good. These don't qualify because this has x to the power of 1/2. We said that's not a monomial, or just root x. Either way, this is not a monomial, so it doesn't qualify. And this doesn't qualify because we have a giant fraction, right? A polynomial is only the sum or addition of monomials. It is not the division or multiplication of monomials. Okay, so moving on. So in general, we can say polynomials fit this general pattern. A polynomial in the variable x, again, like I said, we like to use the letter x. It's a very common independent variable in math, but it doesn't have to be x. It could be any other letter. So a polynomial in the variable x is an expression of the form here. A sub n x to the n plus a sub n minus 1 x to the n minus 1 dot 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 all the way down. So we're supposed to continue in this pattern all the way down until we walk down to a sub 1 times x plus a sub naught. Okay, this is where a sub naught, a sub 1, a sub 2 dot 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 all the way up to a sub n are real numbers, and n is a non-negative integer. Again, that just means it's a counting number. It could be 0, could be 1, 2, 3, 4, right? Any positive counting number. If a sub n does not equal to 0, then the polynomial has degree n. The monomials, a sub k, x to the k power, make up the polynomial and are called the terms of the polynomial. All right, let's do an example of what all this crazy stuff means. So, for example, if I had a polynomial of the form, I'm just going to make one up here, 3x to the 5th power plus 2x to the 4th power plus 8x to the 3rd power minus 5x squared minus 2x plus 7. Okay, so here we have a polynomial where I'm adding 1, 2, 3, 4, 5, 6. There are 6 independent monomials that are being strung together with addition or subtraction, therefore making myself a polynomial. If I only had 2 of them, it would be a binomial. If I had 3 of them, it would be a trinomial. But because it's more than that, then we just refer to it as a generic polynomial. Okay, the biggest degree on our independent variable is this 5, right here, this 5. So this is a polynomial of degree 5. And, the reason they're saying that if a sub n does not equal to 0, this a sub n refers to the constant in front of here. So just to kind of make it match this is saying that this guy right here is n, and then this guy is n minus 1, right? If n is 5, n minus 1 is 4, and then n minus 2 is 3, and then n minus 3 is 2, and then, so on and so forth. Now, this is a generic statement. We don't know where n goes, so it just says dot, 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 keeps going, and eventually, as you walk down, see how we walk down from 5, 4, 3, 2, 1, right? If there's nothing there, by default, there's a 1, then a 0. So this is saying just walk down, reducing powers by 1 all the way down, and eventually you'll get down to, as you walk down, eventually you'll get down to 1, power 1, and then power 0. So we can leave it as a 7, or we can also think of it as 7 times x to the power of 0. Right, so this walks down from 5, 4, 3, 2, 1, power, I would say power 1. So that it's clear, I would say power 1, degree 1, power 1, degree 1. And then we can also think of this x to the 0 power, just so that we have a consistent pattern going from 5, 4, 3, 2, 1, 0. But then, of course, x to the 0 power is just 1, so we can also just not include it there. Okay, now the constants that are in front, like the 3 right here, this is what we refer to as a sub n. Right, so this, in this case, n is 5, so we would refer to it as a sub 5. It's the constant in front of the monomial, or the term that has a degree 5. And this one refers to as a sub 4, and this one's a sub 3, right? So we want the degree here to match that little index. This is just a name, right? A sub 5 is just a name for that one. A sub 4 is just a name. So this little 5 and this little 4, this little 3 is just to help you organize where they belong in this sequence of polynomials. If you think about it, if we just came up with new letters, it would just look really confusing. We do it for a small polynomial, a binomial, a trinomial. We like to assign it different letters. So for instance, when we have a trinomial, it is very common to see it in general this way. Trinomial. We can see it as ax squared plus bx plus c, where we've come up with a, b, and c to represent the constants in front of each term. Or likewise, using this notational style, we could do a sub 2 x to the second plus a sub 1 x to the first plus a sub naught to represent that constant, right? So this would be in keeping with this notational style to represent the same thing as a trinomial. And same thing with a binomial. A very common way to represent a binomial is just going to be ax plus b, right, with degree 1. Binomial, there's just 2 terms. So this can be referred to as just kind of keeping in pace with that notational style. This could be a sub 1 x plus a sub naught. So I think it makes sense that when we have a small number like this, we can assign different letters to the constants, a, b, and c. But I think you could see that if we have a really long one like this one, we'd have to assign a different letter for each one. So if we had ax to the 5th power plus bx to the 4th power plus cx to the 3rd power plus dx to the 2nd power plus ex to the 1st power plus f. Now we have A, B, C, D, E, F, and then, if it's degree 6, degree 7, we'd come up with more and more letters. So it can get really, really confusing to have all those letters everywhere. Now, sometimes we do that, but I think you can see the benefit of coming up with a new notational style, which is this one, right? So a sub 5 refers to the constant in front of the term that has a degree 5. Okay, I think that makes sense now. And so in general, each one of these monomials can also be called terms of a polynomial, the monomials of our polynomial. Okay, some examples. Note that the degree of a polynomial is the highest power of the variable that appears in the polynomial. So here's some examples. So over on our left here, we have polynomials. This one has 3 monomials being added together. Therefore, it's a trinomial. This is an example of 2 monomials being added together. So this is a binomial. This one has 4 terms. So if we continued with this binomial, trinomial, it'd be a quadnomial. But again, we don't really use those terms very much. So we would just call it a polynomial. This one's just a polynomial. There's 4 terms in it. Notice the individual terms, right? So this is, going back here, this is a trinomial. There are 3 terms, and we can identify the terms. So 2x squared is the first term. And then minus 3x is the second term. And then the 4 is the next term after that. Good. All right. Notice that we keep the sign with the term. Good. And this is a degree 2 because the highest power is a 2 right in there. Okay, so now this one is a binomial. There are 2 terms being added. The first term is x to the 8th power. The second term is 5x, so 5x. So there's 2 separate terms. It's a binomial. And the biggest degree is 8. So for that reason, it's a degree 8 binomial, right, in the letter x. Okay, 4 terms. So 4 terms, just a polynomial. The individual terms are the 8 by itself, the minus x, the x squared, and the minus 1/2 x cubed, right? So 4 separate terms. And the biggest degree found is right here. So this is a 3. A degree 3 polynomial in variable x. Okay, next we have another binomial, 2 terms, right? And so 5x is one term and 1 is the other term. Good. And the highest degree, well, there's nothing written, so by default there's a little 1 there. So this is the degree 1 binomial in variable x. Good. The last 2 are monomials, right? So this qualifies as our standard monomial. It's a multiplication of a number times the variable raised to a power that's either a counting number, positive counting number, or 0. And in this case, it's a 5. Okay, so it's a monomial of degree 5 since it's the highest degree that we see. And then finally, just the number x also qualifies as a monomial. The variable is x, so it'd be x to the power of 0. We can include it if we want to, but it's equal to 0, so it's often not included, right? So we could introduce an extra x to the power of 0 if we want to. So this is a degree 0 monomial. All right, moving on. So adding and subtracting polynomials. This is really easy. Adding and subtracting polynomials. So we add and subtract polynomials using properties of real numbers. The idea is to combine like terms. So that is terms with the same variables raised to the same powers using the distributive property. So for example, if we were given this right here, 5x to the 7th power plus 3x to the 7th power, we have 5 copies of x to the 7th plus 3 copies of x to the 7th power. So together we have 8 copies of x to the 7th power. You can think of it in a couple of different ways. So this distributive property here is referring to reminding you that we can also distribute. Remember that if we had say 2 and we had like x plus 5, that we can simplify this by distributing this 2, distributing multiplication across addition. So 2 times x and then 2 times 5. This would be 2x plus 2 times 5, which would then give us 2x plus 10. Right, so this is the distributive property. We're doing the same thing, but sort of in reverse, factoring it. So notice that if I wanted to distribute, I can distribute this way. X to the 7th power times 5 would give us that first term. And then x to the 7th power times 3 would give us this next term. So I can kind of do the reverse of distribution. I can add these things here. So now 3 plus 5, that's just going to be 8. And so I get 8x to the 7th power. Okay, that's what they mean by using the distributive property to add. But, adding and subtracting polynomials in general is pretty easy. You just got to make sure that you are adding or subtracting terms that are identical, that are like terms, and they're like terms because they have the exact same letters and the same powers to those letters, and then we add the numbers in front. Right? So that's really what it boils down to. So here's an example. So let's say I have this trinomial plus this other, a quadnomial or a polynomial plus a trinomial. So here we have one polynomial right here plus another polynomial, right? So this is the summation of two polynomials, right? So here's polynomial number 1 plus polynomial number 2, and we want to add them. To add them, well, we put those parentheses there to identify that there is one copy. So you can kind of think of this invisible 1 out in front here. There's one copy of this polynomial plus one copy of this polynomial. And to get rid of the parentheses, we distribute the 1 across everything. But 1 times anything is just 1. So when there is a 1, we can just kind of get rid of the parentheses without really doing much. So this is just going to be equal to x to the 3rd power minus 6x squared plus 2x plus 4 plus x to the 3rd power plus 5x to the 2nd power minus 7x. Good, so we can just get rid of the parentheses. And now what we want to do is bring together the terms that are like terms, right? They have the same variables and the same powers. So there's an x cubed there, and there's also an x cubed there. We're going to bring those together. There is a term that has an x to the power of 2 there, and a term that has an x to the power of 2 there. There is a term that has an x to the power of 1 there, and 1 over there. And then finally, there's this little 4 here that doesn't play with anybody. Okay, so I'm going to bring them together as x cubed plus x cubed, just writing those together, grouping them together, minus 6x squared plus 5x squared plus 2x minus 7x, and then finally there's this plus 4 out there. Good. Okay, so now these two together give me 2 copies, 2x cubed. And now these, be careful because we have to pay attention to this sign. This is a minus 6 plus 5. We can also think of it as an addition of a negative number, right? So this right now refers to a subtraction of a 6. Subtraction of positive 6. And so that can be the same thing as adding a negative 6. Subtracting a positive 6 is the same thing as adding a negative 6x squared plus 5x squared. I'm just going to copy the whole thing down there. 2x. And then same thing with this. This is a subtraction of a positive 7x. So we can do the same thing and rewrite it as an addition of a negative x plus 4. Okay, and now bringing this down, this becomes 2x cubed plus, and now these two combine to give me a negative 6 plus a 5, that's a negative 1. Negative 1 times x squared. And then same thing here, these two combine to give me a plus 2 plus a negative 7 gives me a plus negative 5, plus negative 5x. And then nobody wants to play with the 4, so we just bring that down. And then finally, we can again rewrite it using subtraction. Addition of a negative 1 is the same thing as subtracting 1. And then addition of a negative 5 is the same thing as subtracting 5. So my final answer is going to be 2x to the 3rd power minus x squared minus 5x plus 4. Okay, here's another example. Similar to the one before, we have a polynomial here. So here is our first polynomial. It has 4 terms, so it's just a generic polynomial. And here's our second polynomial. It has 3 terms, so in particular we can call it a trinomial, but it's still a polynomial. And in this case, we're subtracting it. So before there was an addition there, and just like before, there is no number out in front, so there's just one copy of this polynomial minus one copy of this polynomial. So we can always think of having a 1 in front, 1 times this polynomial minus one copy of this polynomial. Okay, so now when we want to get rid of those parentheses, we're going to distribute this 1 across everywhere. So this equals to x to the third power minus 6x squared plus 2x plus 4. Remember, 1 times anything is exactly the same thing, just 1. And now here we do have to be careful because it's a subtraction, a subtraction of 1. And just like before, we can always think of a subtraction of a minus 1 as an addition of a negative 1. Parentheses, x to the third power plus 5x squared minus 7x. Good. And so now we're going to distribute this minus 1. So this guy here now gets distributed across that parenthesis. Now we're going to distribute and distribute and distribute. And so multiplying by negative 1 is going to change the sign. Okay, so copying the whole thing again, this becomes x cubed minus 6x squared plus 2x plus 4. And when we distribute, we get a plus negative 1 times x cubed plus negative 1 times 5x squared minus negative 1 times 7x. And then again, we can simplify it a little bit more by rewriting it as a subtraction if we want to, and dealing with this subtraction of a negative number, which is going to give us a positive number. So this becomes x to the third power minus 6x squared plus 2x plus 4 minus x cubed minus x cubed minus 5x squared plus 7x. If you want to skip this middle part here, that's fine. I'm just doing extra work to make sure everyone follows those fine little details about changing signs between a negative and a positive. But it's perfectly normal to just skip some of this work or do some of this work in your own head, not necessarily write it down. I'd be perfectly okay if you didn't write down this middle step. Likewise with this next step, if it's confusing you of how to combine addition and subtraction, then you can do as I did before and rewrite it all as addition, where you convert the subtractions into additions of negatives, right? So in this case right now, all of these are referring to subtractions. This is a subtraction symbol. This is a subtraction symbol. This is a subtraction symbol. Good. And we can rewrite it all as addition in the following way. This becomes x to the third power plus negative 6x squared plus 2x plus 4 plus negative x cubed plus negative 5x squared plus 7x. Right, so all I've done is I rewrote the subtraction as an addition of a negative number. I rewrote this subtraction as an addition of a negative number. And I rewrote this subtraction as, again, an addition of a negative number. Good. So now we just have all addition everywhere. So we're going to combine the ones that are like. So we have this term right here and this term right here. Well, they will cancel actually because we have one copy of x to the third power plus negative 1 copies of x to the third power. We could have also seen it over here, obviously. If we leave it as subtraction, x to the third power minus x to the third power, that just becomes 0, right? Okay, so let me write that down. We end up with x to the third power minus x to the third power, which is just going to become 0. All right, now the next term, let's go over here, the x squared terms. So we have negative 6x to the second power plus negative 5x to the second power. Remember that a negative plus a negative equals a bigger negative, right? So this becomes negative 11. We could have also, again, seen it up here, minus 6, if we left it as subtraction, minus 6x squared minus 5x squared. Hopefully, we could have just seen it right there, and we could have gotten the same answer from here. So that just turns into plus negative 6x squared plus negative 5x squared, and together they give you plus negative 11x squared. Good. Next, we have these terms, the terms that just have x to the power of 1. So that's 2x and also 7x, right? So they add up to 9x. That one's an easy one. So we have plus 2x plus 7x. Together, they give you plus 9x. And then finally, there's one term that nobody played with, and that would be the constant 4. It's the only constant, so we can just bring it to the end here. And so our final reduced answer, we don't have to copy down the 0. And an addition of a negative, we can also rewrite that as minus 11x squared plus 9x plus 4. And there's our final answer. Okay, again, let me re-emphasize, I don't mean for you to do it this way when you do it. I'm doing a lot of extra steps because I know some of you need it. Some of you may be a little bit confused about the signs, and I'm just trying to add a little extra information in this section. But if you are comfortable with the signs, there are some very nice, obvious shortcuts you can take. Not only are you allowed to take those shortcuts, you're expected to take those shortcuts. I don't want to see this kind of detailed work, moving forward. Even I, as we move forward, will not show this much detail, in my work as we move forward. Naturally, we can do some of these things, particularly this distribution of a minus. That should be very easy. You can easily skip some of these steps. And then converting a subtraction to an addition of a negative, again, that's not necessary. It's just a nice way of keeping clear what we're doing. If some of you are having an issue, hopefully this helps. But if you're not, then that's fine. You don't have to write down all of this work. So this is what your author did as a solution. So for the first one, we have an addition of two polynomials. Your author brought together the x cubed plus x cubed to give us 2x cubed, and then the minus 6 plus 5 to give us minus x squared, and the 2x minus 7x to give us minus 5x, and then again with the 4. So that's the answer to the first one. And for the second one, same thing. We distribute this minus here, so we see we get a minus, let's come over here. We get a minus 3x, minus x cubed minus 5x squared plus 7x. When we distribute this minus across each of these, the sign changes. And then we combine them. X cubed minus x cubed cancels. Minus 6x squared minus 5x becomes minus 11x squared. And then 2x plus 7x gives you the 9x. Okay, so we get the same answer as before. Okay, multiplying algebraic expressions. So, multiplying algebraic expressions. To find the product of a polynomial or other algebraic expressions, we need to use the distributive property repeatedly. That's one way to do it. In particular, using it 3 times on product, the product of two binomials, we get the following. Okay, so again, remember what we mean by the distributive property. Again, back to if we just had like 3, say y plus 5 like this, we can distribute this 3 this way and this way. And so this is equal to 3y plus 3 times 5, which becomes 3y plus 15. So we're used to seeing the distributive property in this sort of a way. What we're doing here is that we're going to take this and the whole thing has a little unit, and we're going to distribute it across each of these. So that's why we end up with a times c plus d. That would be this guy right here. A times c plus d plus, and then c plus d times b. Right? So we did the distributive property across from the second binomial to the first one. This whole thing times a plus this whole thing times b. That's the distributive property. And then we're going to do the distributive property one more time. This time we're going to take the a and distribute it there. So we get ac plus ad. That's where this and this comes. And finally, b times c and b times d to give us the last terms. So that's how we can figure out the multiplication of two binomials. That's just one way. Some of you guys might have learned a couple of other ways. One other common way is something called the FOIL method. F-O-I-L, FOIL. Okay, so FOIL is just an acronym that helps us remember a particular order in which we multiply things to get the exact same answer. So if you recall, it looks like this. If we have a binomial like this, we multiply the a times the c, that's the f, the first, the outer, the o, the a times the d to give us this, the inner to give b times c to give us that guy, and then the b and the d to give us that guy. So we get the exact same answer, right? This is just pointing out that there's more than one way to think about multiplication of binomials. And there's a couple of other ways. I'm sure some of you might have learned multiplication tiles. If you want to multiply that way, that's a nice way to organize it as well. In general, we can multiply two algebraic expressions by using the distributive property and the laws of exponents. When we multiply trinomials, other polynomials with more terms, we use the distributive property. It is also helpful to arrange the work in a table form. So the next example will give us an illustration of both. Okay, so very important to remember that this FOIL method, let's go back to this FOIL method. This FOIL method is only useful when you're multiplying something of this form. So a binomial times a binomial, you can FOIL it. First, outer, inner, last, that kind of thing. Right, so for example, if I had x plus 2 and I want to multiply it with y plus 3, that fits this form, right? A binomial times a binomial, we can FOIL it away, right? When I learned it, I learned it with a red so that, we have the first, outer, right? So this is the F, the O, the first, the outer, the inner, and the last. And for me, it made a nice red claw. So my teacher would call it the red claw method, right? So, like a lobster, the red claw method. First, outer, inner, and last. So this would give us a way. So the FOIL is just a way of memorizing the order in which you have to multiply things. So the first is x times y. So there's an xy term. Plus the outer. So there's a 3x term. Plus the inner, which is a 2y term, and then finally the last, which is a 2 times 3, so a 6. Right? So this is the answer to this multiplication of 2. But this only works when we have a binomial times a binomial. So now if we had a more complicated expression like 3 plus x plus y times x minus 7, right? There is no first, outer, inner, last in this case because we have a trinomial. So we need a more generic method that works when we have more complicated statements. FOIL is only good for the case of a binomial times a binomial. Good. Okay, so let's do some examples using the distributive property. Okay, so for example, let's say we want to multiply these two polynomials. We have ourselves a binomial times a trinomial, right? By default, if there's no operational symbol between these two, then we have a multiplication. So we cannot FOIL here. There's no first, outer, inner, last because we have a trinomial. It doesn't fit that form. Okay, so we have to use a different method. So first, let's try using the distributive property. So we're going to take one of these and distribute into the other. There's two ways to really think about it. We can either think about this one, that whole thing getting distributed into each of these terms, 1, 2, 3, or we can think of it in the other direction, where maybe we think about this whole thing right here being distributed into each of these. So that whole thing gets distributed into that, and that whole thing gets distributed into that, right? So let's do them both and see what they look like. They both lead to the same answer. So in this way, let's say over here, that means that we would end up with 2x times x squared minus 5x plus 4 plus 3 times x squared minus 5x plus 4, right? So that's where this term right here is the one that's being distributed across that first polynomial. And then if you want to look at it in the other direction, again, now we can look at it as maybe this way. This, oh, let's put a different color to it. This guy getting distributed across each of these terms. All right, I'll put it over here. So put a big or. No, you don't have to do them both ways. I'm just giving you options. So this becomes x squared times 2x plus 3 minus 5x times 2x plus 3 plus 4 times 2x plus 3. Good. And so that's where each of these guys was distributed. The 2x plus 3 times x squared minus 5x times 2x plus 3, and finally 4 times 2x plus 3. Okay, they're both going to ultimately result in the same answer. So next, now we have to continue the distribution process. This time, we have to multiply this times each one of these terms. So 2x times each of these terms. And next, we're going to multiply 3 times each of these terms. And so we'll end up with 2x times x squared, which is just going to be 2x to the power of 3. Well, I'll just spell it all out here. So then we end up with 2x times minus 5x times 2x plus 4 times 2x. Put a little space here, indented, and continue. So then plus 3 times x squared minus 3 times 5x plus 4 times 3. Good. Okay, so then this simplifies as 2x to the power of 3, right? There's a little 1 there, power of 3, minus, and this one is going to become 10x squared plus 8x plus 3x squared minus 15x plus 12. And then again, like before, we can combine some like terms. 2x cubed, there's no other powers of 3, so they don't really combine. And powers of 2, we have a minus 10 here and a plus 3. So minus 10 plus 3 gives us a minus 7. So this becomes minus 7x to the second power. And then the powers of 1. So we have an 8x there minus a 15. 8 minus 15 is negative 7. Negative 7x. And finally, the constant, there's only a 12. So plus 12. Good. Okay, now in this direction, again, we can do the same thing. We can distribute, 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 then distribute, distribute. Be careful to distribute that minus sign as well. And then distribute and distribute. I'm going to do a little bit less writing here. So x squared times 2x becomes 2x to the power of 3 plus x squared times 3 becomes 3x squared. Minus 5x times positive 2x becomes minus 10x squared. Minus 5 times 3 becomes minus 15x. 4 times 2x becomes plus 8x. Plus 3 times 4 becomes plus 12. Good. Okay, so again, combining like terms. Nobody wants to play with the x cubed. It's the only one. So 2x cubed. Then we combine the powers of 2. And there's this one and there's this one. 3 minus 10 is still negative 7. So minus 7x squared. And then the powers of x. We have 15 minus 15 plus 8 is still going to give us minus 7x. Minus 7x. And then we still have this plus 12. Plus 12. Okay. Either way, we get the same answer. Right? You don't have to do it both ways. Just giving you options. And here I did a little less writing. Again, as we progress and you get more and more comfortable, you're expected to do less and less writing. You still have to write down enough for someone to be able to follow your work, but you know, those little details about the signs and distributing a minus, you know, those kind of become second nature, and you don't have to do as much writing unless you feel like you still need it until you feel really, really comfortable with the signs. So for example, here I kind of did it in my head that minus 5 times 2 becomes minus 10, as opposed to kind of rewriting it as an addition of a negative and carrying that along. Okay, let's see what your author did for this question. So yeah, same thing. Distribution, combine like terms, so we get the same answer. All right, one more. How about if we use the table method? Same question, now using the table method. The table method refers to the way we learn to multiply. So if I can remind you that if we learned how to multiply, I don't know, 15, back when we used to use the little x to represent multiplication, 15 times, I don't know, 23, say we wanted to multiply that, we would organize it this way. 23 over 15. Good. In fact, let's make it bigger. Let's make it 232. Okay, so we would automatically put the largest number on top, 232, like this, right? We multiply like this. And then we take turns taking the 5, multiplying it by each of these terms, right? So that would be 10, that would be 0, carry a 1. 15 carry a plus 1 makes it 16. So that's 6 carry a 1. And then 10 plus 1 makes it 11. Then we put a little space holder. Then we multiply the 1 times the 2, the 1 times the 3, and then the 1 times a 2. 1 times 2 gives you a 2. 1 times 3 gives you a 3. 1 times 2 gives you a 2. And then we add them together, so we get 0, 8, 4, 3. So 3,480 is the answer we get when we multiply 232 times 15. Okay, so we're going to do the same sort of thing. We're going to follow the same sort of process when we're multiplying polynomials this way. So I'm going to grab the largest polynomial and put it on top. So that'll be the x squared minus 5x plus 4, and put the other one underneath it. So that would be this 2x plus 3, kind of like that. And again, it's multiplication. So I'm going to take turns multiplying the 3 times each of those terms. So 3 times 4 is a 12. 3 times negative 15, don't forget about the signs, makes it negative 15x. So that's a plus 12. And then plus 3x squared. Good. Now, over here, we automatically put this placeholder here, this 0. But here, we don't have to do that. We just have to make sure that the terms will line up. So the next one is going to be to multiply the 2x times each of these terms. So 2x times 4 is 8x. And instead of putting it right here, I would naturally put it here because that's where there's a term of power 1 for the x. So this becomes an 8x there, and then a minus 10x squared from there, minus 10x squared. And then finally a minus 2x cubed. Not positive 2. Positive 2x cubed at the end there. Good. Let me put some things. Okay, so first we multiply 3 times each of these terms. That's where these guys come from. These guys, these guys, these guys. 3 times each of those. And then later we multiply the positive 2x times each of those terms. So this one, and this one then become this one, and this one. Good. Okay, so next, finally, we combine like terms. So bring it together. We're going to bring down the 12 since there are no other terms with a 12, the constant. And then we have a, this was a positive. So we have a minus 15x plus 8x gives us a minus 7x. Then we have a positive 3x squared minus 10x squared. This gives us a minus 7x squared. And finally, we bring down the 2x cubed. Okay, so we get the same answer as before, just a different organization style. Okay, so this is how your author organized this same thing. Okay, and the last method I want to talk about is something I call the term-by-term method. It's the one I use the most, really. So what we do here is we take each of the terms in the first polynomial and multiply it by each of the terms in the second polynomial. So in this case, we would take the 2x and multiply that by each of the terms in the second polynomial. So multiply 2x times x squared, multiply 2x times negative 5x, and then multiply 2x times 4. And then when you're done with that, then you're going to take each term, the second term here, and you multiply that times each one of the terms in the second polynomial. So this times that, and this times that, and this times that. Right, so this would then become, so you take the 2x, the 2x and multiply it by x squared plus, and then it's 2x times, and it's negative 5x. So be careful to carry the sign over. And then plus, and then it's 2x times 4. Right, so then that's, let me highlight this. This is the 2x being multiplied by each term in the second polynomial. And then we continue that on with plus, and now it's 3 times x squared plus 3 times negative 5x plus, and then 3 times 4. 3 times 4, right? So then here's the 3 being multiplied by each of the terms in the second polynomial. So then we just simplify that. So this would be 2x times x squared gives you 2x cubed. 2x cubed minus 10x squared. 10x squared plus 8x plus 8x plus 3x squared minus 15x plus 12. Good. And then you combine like terms, as usual. There were no terms with an x cubed. This term and this term combine, and also this term right here, and this term combined. They both have power 1. And there are no other constants except the 12. So then we combine like terms. So we have 2x cubed, and then minus 10x squared and plus 3x squared gives us minus 7x squared. And then plus 8 minus 15x gives us minus 7x plus 12. So there's our final answer. Okay, special product formulas. there are some special cases, some I wouldn't say special, they're common, things we run into all the time. These are 5 very well-known, very common formulas that come from multiplication. So let's explore each one of these. So a plus b times a minus b equals to a squared minus b squared, sum and difference of the same terms, right? So where does this number 1 come from? Let's explore it. So number 1 comes from, if we had a plus b times a minus b, right? So a plus b times a minus b. We can think of this using, or we can solve this using our good old FOIL method. First, outer, inner, last, our red claw method. So if we do that, a times a becomes a squared. A times minus b becomes minus ab, right? This is from the first and the outer. The inner is b times a, or a times b, so this is plus ab. And then finally the outer is negative b squared, right? So this is the first, the outer, the inner, and the last. So this is the first, the outer, the inner, and the last. FOIL. Okay, and what happens is that in this particular case, the 2 terms in the middle cancel out. Minus AB plus AB, they cancel out. And so our whole thing just becomes a squared minus b squared. So that's where that first formula comes from. Whenever we see something of the form a plus b, a minus b, then we can say, well, we could FOIL it all out, or we notice a pattern, right? A pattern is just to say that this is just going to be a squared minus b squared, right? For example, if I had x squared plus 7 times a squared minus 7, I can recognize that this fits this form, where the a is an x squared, the b is a 7. Good. And if I wanted to FOIL this out, I could do that, or I can save myself some time and realize that it fits a certain pattern. This fits this particular pattern, so I know my answer is going to be x squared squared minus 7 squared. Good. So in this case, I know the answer is just going to be x to the 4th power minus 49. Good. And so that's where that first one comes from. The a plus b times a minus b simplifies to a squared minus b squared. All right, let's take a look at the second one. The second one is a plus b squared equals this little formula. Let's look at that. So now if we have a plus b squared, then this is the same thing as a plus b times a plus b. And again, if we FOIL, first, outer, inner, last, our little red claw, then this is going to be equal to a squared for the first term, a times b plus ab. The inside to the inner is also going to be a times b plus ab, and the outer is plus b squared. So when they had opposite signs, a plus and a minus, the middle term canceled, but because there's pluses there, the middle 2 terms add together. And so this gives us an a squared plus a 2ab plus b squared, and that's where the formula comes from. That a plus b parentheses squared, if you see something that fits this form, then I know that the answer is just a squared plus 2ab plus b squared. So it's the first term squared plus the last term squared at the end, and the middle is twice the multiplication of the 2. Again, for example, if we had 7x plus y parentheses squared, again, this fits this form. I could FOIL it all out, or I could say, well, it fits a form. I know a pattern. So this is 7x parentheses squared at the beginning, the first term squared, the last term squared at the end. So let's put a plus y squared at the end there. plus the middle is twice the two different terms that you're in your binomial. Twice 2 times 7x times y. So then this just simplifies to 49x squared plus 14xy plus y squared. Good, so it's just a pattern that we can recognize, a shortcut that we can use. Good, so that's where that second one comes from. The third one is almost identical. If we had a minus b parentheses squared, well, this is a minus b times a minus b. Again, if we use our little FOIL, F-O-I-L, our nice little red claw right there, then this becomes a squared minus ab, right? So positive a times negative b. And then we have negative b times positive a, so we have another term of a minus b. And then a negative times a negative becomes a positive, so that becomes plus b squared. Good. So when they had opposite signs, when we had a plus and a minus, the middle terms canceled. That was the first one we looked at. When they both have pluses, these two terms add, and in this case, they both have subtractions, so these things add and keep the negative sign. So this becomes a squared minus 2ab plus b squared. Good. So again, that's the pattern that we noticed, that if we have a minus b parentheses squared, if we see something that fits this form, we could FOIL it all out, or we can recognize that a pattern is formed and we can jump to an easier answer. So for example, if we had a complicated statement like w cubed plus 4xy cubed minus 4xy squared, again, we could FOIL the whole thing out, or we can recognize a pattern. This fits this form where this is the a and this whole crazy thing is that b. So this is going to be w cubed parentheses squared, the first term squared. Now at the end, it's a plus, because the pattern says plus, because the minuses are going to cancel. So it's plus parentheses 4xy parentheses squared. And in the middle, we have a minus 2 times each of the things that you were multiplying. So that would be 2 times w cubed times 4xy. Good, so then this simplifies to w to the 6th power minus 8w to the 3rd power xy. So that's 2 times 4 gives you 8, and then the other terms can't simplify, so we just bring them along. Plus, and now this becomes 16x squared y squared. Good, so it's just the pattern that we recognize. Let's go back to the table. Okay, so we've kind of looked at where the first three come from. The last two are just something that you can get by multiplying them again. So if we multiply, let's look at a plus b to the power of 3. So if we have a plus b to the power of 3, this is the same thing as a plus b times a plus b times a plus b, right? So we already know what the first two are. The first two are a plus b squared times another a plus b. And we already know that this pattern here for this one exists. This is going to be a squared plus 2ab plus b squared. And then we just have to multiply that by a plus b one more time. Okay, so we're going to do distribution. Again, I'm going to distribute this way. I'm going to distribute this term into each of these, or I can distribute this term into each of those. So let's do that. I'm going to multiply this whole thing right here is going to be distributed times an a, and then that whole thing times a b. So this will be equal to a squared plus 2ab plus b squared times a plus a squared plus 2ab plus b squared times a b. And then we're going to do distribution one more time. distribute there, distribute there, distribute there, and then distribute there, distribute there, and distribute there. So we'll end up with a to the power of 3 plus 2a squared b plus ab squared. Right? So power 3 for the a, 2a squared b plus ab squared. Plus, now we distribute this b, we get ba squared plus 2ab squared plus b cubed. Okay, so now combining like terms, making sure that they have the same letters and the same powers on those letters, we see that a squared, this one has an a squared and a b. This one has an a and a b squared, not the same. But this one has the same thing, one copy of a squared and a b. So those two are like terms. And likewise, this one has an a and a b squared, and this one has an a and a b squared. Those two are like terms. So these two are going to add up to 3, and these two are going to add up to 3. Right, since there's this sort of this invisible 1 right in there. So our final result is going to be a cubed plus 3 copies of a squared b plus another 3 copies of a b squared plus b cubed. And so there's our pattern that we notice. A plus b parentheses cubed is equal to this. Okay, you can do the same thing for the last one. Okay, so these are just 3 very commonly used formulas that help us multiply things out or expand things out in an easier way. And then later, we'll also be asked to go backwards down the road. So it's nice to know these shortcuts when we're multiplying, but it's very important when we want to go backwards in a process called factoring to be able to go backwards, to be able to go from the right-hand side to the left-hand side. But for now, we're just going from the left-hand side to the right-hand side. Okay, let's look at a couple of examples, a couple more examples where we use these formulas. Okay, so let's, for example, look at this case where we have x squared plus y cubed, parentheses, raised to the power of 2. Again, like before, we could just FOIL it all out. We could say that this is equal to x squared plus y cubed times x squared plus y cubed. And we could do the FOIL thing and multiply this times this, and this times that, and this times this, and this times that. We get ourselves a nice red claw. FOIL it all out, multiply it all out, we'll get the correct answer. But the goal of this is to realize that there's an easier method where we can just recognize that it fits a particular pattern. Okay? It fits a particular pattern, right? So if we realize that this fits the form of a plus b, right? This could be the a, this could be the b in the form a plus b squared. And we know from our formula that that means that this is a squared plus 2ab plus b squared. Then we can just jump right to our answer in this way. So x squared plus y cubed raised to the power of 2. So the a is this x squared, the b is the y cubed, and so it expands this way. So a squared, right? So then from there we could just simplify it and say our final answer then is going to be x to the power of 4 plus 2x to the power of 2y cubed plus y to the power of 6, right? So it's just a nice little shortcut to foiling in this case. But like I said, later on we will be going backwards to foil this, factor this process. And then this these special product rules become very, very useful. Okay, a couple more examples. So for this one, again, we realize that we have 3x plus 5 raised to the power of 2. We can FOIL it all out, but we want to use our rules, our little shortcut rules, our product rules. So if we realize that this guy right here plays the role of A, this guy plays the role of B, and we're squaring it, that tells me that this is going to be 3x parentheses squared, the first term squared. I always like to do it this way. I put a plus, and then I put a little space there, and then the last term squared. Right? It's the first term squared plus the last term squared at the end, and the middle is twice the two things that you're squaring. Right? The two terms. Just the way I like to organize it. Anyway, so this becomes 9x squared for the first term, plus 2 times 3 is 6 times 5 is 30, 30x, plus, well, the last term is 25. So there's our answer. Okay. Okay, now for this one, we notice that it's a x squared minus 2 raised to the power of 3. So if we think of this as our a, and this one as our b, this is a minus b to the power of 3. And from our formula, we know that this is equal to a cubed there. There's going to be a 3a squared b there. There's another 3ab squared there, and then there's a b cubed there, and there's a plus minus situation going on. Okay, so we want to use this formula. So using that formula, we can say that this answer, I'm going to squeeze it over here, x squared minus 2 raised to the power of 3, then becomes a x squared raised to the power of 3 minus 3 times x squared times 2 times 2 plus 3 times x squared times 2 squared minus 2 to the power of 3. Good. So keeping the signs, let's come back over here, point that out. There is a minus there, that's why there's a minus there. There's a plus here, there's a plus there. There's a minus there, there's a minus there. So this little formula already takes into account that this is a subtraction of a positive 2. This is a subtraction of a positive 2, subtraction of a positive b. So that's already taken into account into those signs there. So I do not carry this minus into here, for example. So it would be wrong for you to put a minus there and to put a minus there and to put a minus there, because the formula has already taken into account. If you were foiling this all out on your own, you do have to take that into consideration. But this is just recognizing a pattern and recognizing that the pattern has already taken that into account. That's why there's a minus here. That's why there's a minus there. Okay, all right, so hopefully you don't make that mistake. And so now we can simplify this whole statement and say that x squared minus 2 to the power of 3 is x to the power of 6 minus 6 x to the power of 4, that's this term. And then 3 times 2 squared makes it 4, times 3 makes it 12, plus 12 x to the power of 2 minus 8. So there's our answer. Okay, let's see what your author did for this one. So yeah, we should get the same answers. Okay, so hopefully that's enough to help you get through your homework. If you have any questions, please let me know and come by my office hours.